Hello guys, today we're going to discuss about a problem called validate binary search tree. This problem is present in many coding platforms like Leetcode, HackerRank, or Signal, etc. Because the reason why it is run in each and every platform is it is very famous interview problem. It is asked in many tech companies. So that's the reason why I thought of explaining this problem. So before jumping into the problem, let's discuss about binary search tree. So binary search tree is nothing more. It is a normal tree. That's it. There's nothing much difference. The only difference between them is between normal tree and the binary search tree is uh, all the elements to the left subtree will be less than the root node, and all the elements to the right subtree will be greater than the root node. So you can clearly see in the second line. See, the left subtree of node contains only nodes with keys lesser than the node's key. And similar to a right subtree, the right subtree of a node contains only nodes with the keys greater than the node's key. I'll show you an example here. So this is a binary search tree. So let's start from 8. So let's if you clearly observe here, all the elements in the left subtree of 8 are lesser than 8. See, 3, 1, 6, 4, 7. All these elements are less than 8. And if you clearly observe in the right subtree, 10, 14, 13, all these elements are greater than 8. So that's the reason why this is binary search tree. And not only this theory should happen in each and every node. For 3, for 10, for 6, for 13, for 14. See, for 3, 1 is in left subtree, which is less than 3. For in the right subtree, 6, 4, 7, which is greater than 3. So that's why we can say this is a valid binary search tree. I'll show you an example of invalid binary search tree. See, uh, coming from 30, the left subtree contains only 5, which is less than 30. This is okay. But if you come to right subtree, it contains 10, 40, 15. So if 10 is less than 30, right? But it shouldn't be in the right subtree. It has to be in the left subtree. So that's the reason why I'm telling this is not invalid binary search tree. So this is the main asset of this problem. By verifying this, we can achieve the problem. So the way we achieve the problem is doing in-order traversal. And the way we do in-order traversal is first going acquiring the left subtree and coming to the root node and acquiring the right subtree. So this is what this is what the rule is. So first you need to go to the left subtree, and we need to acquire the root and go to right subtree. So I'll show you the example. So first will be in 8, right? So first we need to go to left subtree. We'll go here, and again we need to go left from 3. So 1 doesn't have any left subtree, right? So we need to acquire the root. So we got 1 first. 1 doesn't have any right subtree, right? So we need to go back again to the 3. So now we need to acquire the root node, which is 3. So we got 3. Now we have to go to right subtree. Now 6 has a left subtree, so we need to go for left subtree first. Go left. So 4 doesn't have any left subtree, right? So now we have to come to root node. So now we can acquire fourth. Now 4 doesn't have any right subtree. Now we can go back. Now we are complete with the left subtree of 6. Now we need to acquire 6. Now we need to go to the right subtree of 6. Now 7 doesn't have any left subtree, so that's the reason why we can directly acquire 7. 7 doesn't have any right subtree. We can go back. And we're done with 6. We can go back. We are done with 3. We can go back. Now we complete the left subtree of 8. Now we need to acquire 8, right? So we got 8 here. And now our job is to go to right subtree. So we go to 10. So 10 doesn't have any left subtree. Now we need to acquire 10. So 10 does have right subtree. So we need to go to 14. And 14 does have left subtree. We need to go to 13. Now 13 doesn't have left subtree, right? Now we need to acquire that the root, which is 13. And 13 doesn't have right subtree. Then we can go back. Now we are done with left subtree of 14. Now we need to acquire 14. Now 14 doesn't have any right subtree, and we can go back. And we are done with 10, and we have to go back. and we are done with the whole binary search tree. So this is how we can do an in-order traversal. And you can clearly observe here, if you perform an in-order traversal in a binary search tree, what happens is everything will be in ascending order. See, 1, 3, 1, 3, 4, 6, 7, 8, 10, 13, 14. Everything will be ascending order. Only if it is valid binary search tree. If at all it is not valid, then they'll not be in ascending order. So with this concept, we can do this problem by just verifying whether its previous element is smaller than the current element. So there are like different approaches for this. One thing is storing your in-order traversal in an array and verifying whether its previous element is smaller than the current element. So for this approach, the space complexity would be order of n because you're storing it, right? So if you bother about space complexity, you can optimize this without using any space. So that would be like order, like constant space. So we always choose best solution. So let's go with the best one. So the way we perform that is we can like use a variable. You can use like a variable called last printed. Now we'll have a variable called last printed. Let's say it LP. So for initial it is null because we haven't visited anything yet. So first will be at 8, right? So for 8 we'll go to its left subtree. So 3 have a left subtree. We'll go to 1. 1 doesn't have a left subtree. So now we can verify if at all there is something we have visited before or not. So we haven't visited before because it is last pointer is null. So there's no need of verifying anything. So we can directly put the last pointer is equal to 1 and we can go back. And now we need to verify whether the last printed, which is 1, is more than 3 or not. Definitely 1 is more than 3, right? So we can move forward and we need to change the last one is 3 and we need to go to his right subtree. And 6 does have left subtree. We go to 4. 4 doesn't have right subtree, left subtree. So now we need to verify whether the last printer, which is 3, is less than 4 or not. Definitely 3 is less than 4. So we can move on. So we need to change like the LP to 4 and we need to continue with our traversal. And we come to 6. So we need to check again like 4 is less than 6 or not. 4 is definitely less than 6. So we can move on by changing this to 6. Now we can go to 7. The same thing happens everywhere. Now we need to verify 6 is less than 7. Just 6 is less than 7. We need to change it 7 and we need to go back. We're done with 6. We're done with 3. Now we need to go to 8. And now we need to verify whether 7 is less than 8. Definitely 7 is less than 8. Now we can change to 8 and we need to move on. So 10 doesn't have any left subtree, right? Then now we need to verify whether 10 is greater than or 8 is less than 10. Definitely 8 is less than 10. Then we can change it to 10 and we can move on to its right subtree. Now 14 does have left subtree. We need to go to left. Now 13 doesn't have any left subtree. Now verify whether 13 is greater than the last printed one. Definitely it is greater than the last printed one. Now we need to change it to 13 and go back. Now we need to verify 14 is greater than the last printed one. Yes, it is greater than. So we can change it to 14. Now we can go back to 10. We can go back to 8. So with this we can clearly observe that everything is okay. So that's the reason why it is a valid binary search tree. So if at all it is not valid, the last printer will be greater than or some interruption will be present. I'll show you with this example. So in this what happens is let's take like last printed is equal to null. So first we'll come to 30. We'll go to 5. So 5 doesn't have any left subtree. So now we need to verify whether 5 is less than the last printed one. As we haven't visited anything yet, there's no need of verifying. So we can directly put 5 to last printed. Now we need to go back. Now we need to verify whether 30 is greater than the last printed one. Of course it is greater than. We can move on. Now we can change it to 30. Now go to right and go to left. 10 doesn't have any left subtree, right? So we can now is the main asset for this problem, which see you can clearly observe the last printed one, which is 30. It is greater than the current value, which is 10, right? That shouldn't be the case, because in binary search tree the last printed should be always less than the current one. So in this time we can directly say that this is invalid binary search tree. So this is how we can validate a binary search tree. So the way we implement this problem is exactly same how I explained before by using a variable. So I'll use the same thing, starting with the variable called LP is equal to null, as I have initialized before while explaining. So verify if root is equal to null. If root is equal to null, you can directly return true, because only root is always binary a valid thing. So as I've said you before, first like we need to go to left, and we need to print, or we need to use root, and then we go to right. The same thing I use here. So if not valid of bst of root dot left, return false. So the thing is, if at all we get false, so there is no need of going to right subtree, right? We can directly return false. That's why I have used this. So now we need to verify whether last print is not equal to null, and if last print is greater than or equal to current value. If at all this satisfies, then that means it is not valid. Return false, because the last printed should be always less than the current value. And the main thing is we need to change the last printed value, which is current value. And the same thing happens in the right subtree, which is valid bst and root dot right. If it all returns false, return false. If everything goes well, return true. So this is pretty much the complete problem. Let's see if at all I have any errors. Okay, integer, validate, return true, return true, return true. Okay, let's see. Okay, it worked. Let's submit the problem. Okay, we are done with the problem. So this is how, guys, we do validation of a binary search tree. If you have any doubts, you can comment down below and make sure you like, subscribe. Thank you.